All right. Okay. Well, I just have a couple I have first I have this uh hierarchical regression model that uses R2JAGs, which allows us to kind of sample our um the coefficients for a regression model. So using I guess Bayesian inference here. And so this is an example. And here, I'll talk through all of the different elements. And then after we work through that, I've posted to Brew and Learn. I've posted this PDF that says Gibbs sampling for the uninitiated. And it works through this kind of document clustering model, which I will demonstrate for you guys as well. Well, I don't it'll take a while to work through it. So we might not finish all of it today, and then I guess we'll save the rest for it during 10th week, just because there's a lot to kind of set up and explain. So, but anyway, that's what we have planned for today. So, anyway, let's go ahead and take a look at this regression model. And so to get this to work, we have to kind of you have to have JAGs installed, MCMC, um, you know, uh, JAGs there, and then what we're gonna do is um, I'm gonna just create an artificial data set here. So I'm gonna say a number of simulated points will be 100, and I'm going to just generate some x1 values and some x2 values. X1 will come from a normal distribution, and X2 will come from a binomial. This is just kind of, um, I guess, a Bernoulli. Uh, some of it will be yes and no, and then we have some error. Okay. And so basically, there is a X1 is a continuous variable. X2 is a discrete. It's either, you're in group one or group two, where around so if you look at the variables of x1, it's just a bunch of these, this type of number, whereas x2 is zeros and ones. So you're either in group one or group two, and we don't have an interaction effect, but we have, we have some random error here, and this will be our true model. So I'm just making up some coefficients. I just arbitrarily chose these. But we're going to put a slope of 1.2 for B1. And then we'll say if you are in group one, then your score will be reduced by around negative 3.1. There's an intercept of 1.5, and then each individual data point, we have y here, okay? So here is our simulated data. And then here, let me just kind of create a plot. Let me do okay, I'm going to do SimDat. So this is what our data look like. And then so let me see. ggplot, what do we want? We want AES. Um, okay, we're gonna do y equals y, x equals x1, and then I'll do color equals x2, data equals SimDat, and then let's do genome underscore point. Does that work? Okay. So this is kind of what our data look like. So we've got a, uh, I guess this overall slope would be 1.2. Oh, you know what? The color should be I guess categorical, but anyway, we've got some zeros and ones. If group zero is up there, group one is down here. Um, and so we could see we have two parallel lines and one is higher than the other. Okay, if we fit a frequentist model, we would just use LM. LM, we would just do y as explained by x1 and x2. Let me redo my x2 as a factor. Okay, let me see. Two is not meaningful for factors. Okay. And is that what we do? No, plus is not me. Oh, I guess I gotta do B2 and then as numeric. See if this changes anything. Great. It looks the same. But yeah, now it's a factor, and then we're gonna fit a model here. Y is explained by x1 and x2. And then here is our okay. And so these are the estimated coefficients. Um, so the true values for the intercept was 1.5, and it's estimated to be negative 1.25. Okay. The true value for the slope is 1.2, and it's estimated to be 1.135. And then the true value for the kind of the difference coefficient is negative 3.1, and it's getting that pretty spot on at negative 3.09. Okay. So that's how a frequentist model works. Let me see if we can get this to work here. And x2 simulated data is going to be x2, and then let me just call this in here. Okay, so I'm gonna have to do this. Okay, so now I'm gonna set up a model using a Bayesian model. And so we're gonna say there is oh, you know what? I have this incorrect. Well, anyway. Um, so the way this works is we calculate for each observation, we do alpha plus beta times x1 plus beta 2 times x2, and then we add in a random bit of error here, okay? And that's going to explain kind of our matrix Y. Our intercept, okay, is going to have a mean of 0. And then this is kind of, it's a little bit weird. In JAGS, instead of specifying your standard deviation, you specify kind of the inverse of that. So this is kind of like having a, I think a standard deviation of, like 10. The inverse variance here. So, alpha could be anything from negative 10 to, or I guess negative 30 to positive 30, 99.7% values there. We're going to say beta. We're putting in kind of very kind of uninformative priors. and we're saying our slope value could be anywhere from negative 100 to positive 100, where the true value is like 1.2. And then for beta 2, it could be anywhere from negative 100 to positive 100, where the true value is negative 3.1. Now, obviously, if you had a little bit more information, where instead of just saying it could be anything from negative 100 to positive 100, you could include that in there, and that would, better guide the, your inference there. Okay. And then as far as what tau is going to be, as far as our thing, um, I'm using a gamma distribution. So this is going to have a kind of a big variance there. So I'm going to specify my model as such. We'll bring in our data, which is coming from our data set. Y, x1 is this, x2 is that. This is how many rows we have. This is the parameters that we want JAGS, the Bayesian inference, to perform on. Or this is, I'm sorry, the data, the list of data, and these are the parameters that we want inference to be performed on. So hopefully this works. I'm going to run 3 simultaneous chains using JAGS, and that it is running here. And it's done. Okay, so let's see if it got it right. Okay, so our true values, let's see, our true value for alpha, or I guess here, let's compare it to our frequentist model. Okay, so the frequentist model, its estimate is negative 1.25 in our Bayesian model. The median is right around the same, negative 1.257. Okay. But again, with the Bayesian model, we kind of sample a bunch of values and we say, you know what, 95% of my values, as far as what alpha could be, is in between negative 1.8 and negative 0.7. Okay. As far as our beta values, okay, the frequentist model, when we fit LM, we got 1.135, and we get right around the same value when we do Bayesian inference, but then we also kind of get a 95% range of saying 95% of our values are in between 1.034 and 1.236. So we're saying, the resulting, whatever the posterior distribution, looks kind of like this. Okay. And then as far as our beta 2 coefficient, it estimated to be negative 3.09 using LM, and our Bayesian model also gets negative 3.09, but also provides a 95% range, saying it could be anywhere from negative 3.5 to negative 2.679. So we get, rather than just kind of pinpoint estimates that says like this is going to maximize your likelihood, which is fine, we get a distribution of what the values could be, and that's the resulting Bayesian model fit. Okay, using JAGS. So it performs Gibbs sampling. It performed kind of 3 simultaneous chains. Here's a plot. This is basically our confidence, not our, actually our confidence intervals, I guess our probability intervals. 80% probability intervals. So we're saying, beta 2 is right around negative 3.1, and somewhere in between here and here is kind of our range there. And then you can also see the trace plots for each of our different coefficients that we estimated. And so we could see, they bounce around all over the place, centered around negative 3.1, but sometimes a little bit higher, sometimes a little bit lower. And these are all, performed via Gibbs sampling here. So anyway, that is how you could go about. So you can kind of use this as a template to kind of get started if you wanted to fit a linear regression model um, using a a Gibbs sampler or Bayesian inference. And you could further refine this. So for example, let's say you knew, let's say you knew your beta 1 coefficient, you know, should be centered around, I don't know, 1, okay? And you can kind of specify it this way. And if that were the case, you could specify your model that way and you'd fit it, and that's going to kind of refine what your values will be. So, how does that compare between 1.03 to 1.234? Yeah, it's pretty similar. So at this point, I guess we have enough data to perform pretty good inference. Um, but uh, but I guess, if your preconceived notions were, way off, like let's see, if I specify it to be 10, it might not do as good of a job fitting. But again, we might have enough data. Yeah, no, even if I have my initial specification pretty far off, I guess I have enough data with 100 observations that I can kind of rely more heavily on the data there. Okay. But anyway, this is how you could go about fitting a regression model there. Okay. Now let me bring walk us through this paper, Gibbs sampling for the uninitiated. And in this paper, what they do is they create a hierarchical model. Okay, a hierarchical model for a document clustering setup using Bayesian inference. Okay, which is kind of neat. Okay, so um, so anyway, it goes through the beginning part, just kind of um, talking about a lot of stuff that we've covered. So it says, Markov chain Monte Carlo techniques like Gibbs sampling provide a principled ways to approximate the value of an integral, and then it kind of and then it goes into, like, why do we want to bother with integrals? But I'm going to kind of go ahead and skip through all of this, and um, you can read through this as you see fit. Um, but this is what we want to do, is that we want to create a document clustering algorithm here. And so this is kind of how they write their Gibbs sampling algorithm. And so this is uh, I guess just the format. And they say, hey, if you want to sample z sub I, okay, then you're going to for you use the latest values from z1 through zi minus 1 at time t plus 1, and then the other values which you haven't sampled yet, which are values from zi plus 1 through zk, you use the latest values that you have at time t. Okay, and this conditional probability can be calculated by doing basically this the joint probability of everything, including zi at time t, divided by the joint probability of everything excluding zi at time t. Okay, and that's how you would get the conditional probability. Okay, so it says, notice the only difference between the numerator and the denominator is that the numerator is the full joint probability, including zi at time t, whereas zi at time t is missing in the denominator. Okay, so that's how they say this is how you would set up your conditional probability. Okay, so they're going to say, now that we have this set up, we are going to create um, a model for how documents are generated, and then we're going to use that to cluster our documents. Okay, so I guess maybe I should back up and and we will back up and say, you could create a document clustering program, and what this would do is it would kind of, um, I don't know, I suppose you could download a bunch of newspaper articles, okay? And then based on the vocabulary, the words used in each of these articles, can you form clusters? And can you say, okay, we're going to um, group these documents together because they use similar words. We're going to group these documents together because they use similar words, and so on and so forth. There is a slight difference between a document clustering algorithm and a document classification algorithm. So a document classification algorithm would be kind of a supervised learning problem where you kind of already know some of the categories, and you probably already know some of the vocabulary. So in a document classification algorithm, you might say we have these um, documents and try to figure out if this document is about politics or if this document's about, if this article is about business or this article is about, um, world issues or things like that. Okay. And so, um, and you'd say, if it's about politics, certain words like president, government, and senator will have higher probabilities. If it's about business, you'll other words like earnings and stocks and market will have higher probabilities. And then if it's about world news, things like country and I don't know, conflict and things like that will have higher probabilities. And you would kind of go through each document and you would look at the word probabilities and you would classify them. Okay. So the document clustering algorithms are similar in that you do want to kind of group the documents together based on the words. However, you don't have these kind of predefined categories that say, hey, I want to create a category for politics and a category for business and a category for world news. Rather, it's just it's what we call unsupervised learning, and we say, hey, here's a bunch of documents, and I want you to form two piles, or I want you to form three piles of documents, and try to group them together so that similar documents are together. So it's a little bit tougher because you don't know like what the categories are to begin with. You're just given the instructions, form, two or three piles where all the documents are similar. Um, and so how do we explain what a document is? Okay. So the document is going to be treated as a what we call a bag of words. Okay, we're gonna have a bag of words um, model for our document, and so um, okay, what we're gonna do is we are going to say so we're gonna start off with a simple case, and we are going to cluster. We're gonna have basically a pile of documents, a pile of articles or whatever, and we're going to try to form two clusters. Okay. And we will call these clusters 0 and 1. These are going to be our classes or, labels or whatever. Okay. So it says sometimes we'll refer to 0 and 1 as classes or labels. And so we have some document. Okay. The document is this treated as a bag of words. And we're going to, once we take the document, we're going to just assign it the name vector, the vector which is named W sub j. Okay, so a bag of words model is just imagine, in a cartoon, you have a piece of paper. Okay. So I have this, okay. I have this piece of paper, and just imagine like in a cartoon, they shake the paper and then the words fall off the page. Okay. And then you've gathered those words into a bag. And and the idea here is that the order of the words don't matter. It's just the count of the words. Okay. So you just um there are certainly limitations with a bag of words model because order of words certainly do matter in a lot of cases. But here we're going to just take the words and look at the count of the words. And based on the count of the words, can we cluster the documents together? Okay. And so um, we have two classes or two labels, class 0 and class 1. And all of the documents that have class 0, okay, are gathered together into what we call big C of 0. This is a corpus, okay? So it says it it will be convenient to refer to the set of documents sharing the same label. Okay, so C0, corpus 0, will be all of the documents gathered together that have label 0. And then corpus 1 will be all of the documents gathered together that have label 1. Okay, and um, and so what we want to do is we want to figure out based on if we have a new document coming in, okay, some document with, word counts in this vector W. So it'll say like, the word house shows up twice and the word dog shows up once and the word, I don't know, some other word shows up 0 times and another word shows up 3 times based on the word counts. Okay. And so this word vector might be very long because you might have a big vocabulary of like thousands of words. And a lot of these counts will have 0, and some of these counts will have, 1 or 20 or whatever, however big your document is. But based on that vector of word counts, can we figure out what is going to be the most probable label? Okay, that's argmax for P L of W. So what is label 0 the most probable, or is label 1 the most probable? Okay, and label 0 is so if we do this using Bayes' rule, we can say um, the label that will maximize this thing, the posterior probability, okay, is going to be the same label that maximizes Bayes' rule, which is going to be the probability of the word vector given the label times the prior probability of the label, okay? And then we just ignore the constant at the bottom because we're just trying to maximize this. So if you have a function and and it's being divided by a constant, then the same value that maximizes, the function multiplied by the constant is going to be the same value as the the value that maximizes the function without the constant. So we could just safely ignore that constant on the bottom. So we just want to know, okay, what is the probability of this word vector given a label times the prior probability of the label? So how do we think about, the words being generated? Okay. Here's a diagram kind of explaining this. This is the plate diagram. And we're going to basically, as far as our document goes, this is going to be drawn from a multinomial probability. Okay. We have a Bernoulli probability, a Bernoulli distribution generating our label, a 0 or 1. And then once we have a 0 or 1, we will generate uh, a vector of words using a multinomial. Okay. Now that multinomial probability depends on our vector of probabilities, theta. Okay. So this is what we have here. So let me just kind of explain. I don't know if are you guys familiar with the multinomial probability? Maybe.
No, if you could explain it.
Yes, I will explain the multinomial probability. Thank you. All right. So, well, we are familiar with the binomial probability, right? So binomial probability. Okay, actually. Um, so if I say, let's generate something from the binomial probability, we would say, if I want one value, and I'm gonna, hold on, I gotta look up the size and probability. Okay. So it's gonna be like 10 words, or 10 things, and my probability is, I don't know, 0.5. So this would be, I'm gonna flip a coin 10 times. The probability that the coin lands heads is 0.5. How many times do I get heads? Okay, and so I do R binom, and it says I flipped the coin 10 times, and I got heads 6 times. Okay, so this is like coin flips. Um, Coin flips with maybe possibly, unfair coin. So you could put in, probability 0.7. I'm going to flip it 10 times. How many times does it land heads? It says it landed heads 8 times. If I flip it again, it landed heads 9 times. It landed heads 6 times. Okay, so that's binomial. Okay, multinomial is basically dice rolls with an unfair die. Okay, so let me. What is I don't I have to look up how do I do multinomial probabilities in R. The multinomial distribution, mul R multinom. Did I not? Okay. Okay, size n and size probability. So this time, so imagine a die. Okay, die has I don't know, let's say and you could have let's have a 10-sided die has probabilities, or actually let's make it simpler. Okay, a 5-sided die has probabilities, I don't know, point two. One of the sides is only 0.1. Another side has probability 0.4. How much do these add up to? Okay, and then the last side has probability 0.1. Okay. So this will be a vector of probabilities, and I'm going to roll this unfair die 10 times, and I want to know, okay, how many times did each side appear? Okay, and so this is the output. It said you had a 5-sided die with these probabilities, and you rolled it 10 times, and the number 1 showed up twice. The number 2 showed up 0 times. The number 3 showed up 3 times. Even despite having only a probability of 0.1, that's fine. Okay. This side showed up 3 times. It had a probability of 0.4. And this side, despite having a probability of only 0.1, it showed up twice. Okay. I could say, hey, let's try that again. And this time I got something a little bit closer to what I might expect. The expected would be 2, 2, 1, 4, 1, and I got 2, 1, 2, 4, 1. And if I generate it again, I got 2, 1, 0, 6, 1, right? And, I could say, hey, I want 10 of these things. So I rolled it 10 times and it counted how many times I got each side, 10 times, and it counted up how many times I got each side. And so we could see consistently side 4, which has the highest probability, shows up the most frequently. Okay. And then sides 3 and 5 show up less frequently, and these show up less frequently also. Okay. And then, these show up. All right. So that's a multinomial probability. All right. Does that kind of clarify? I hope. So binomial probability would be flipping a coin and you're just counting the number of heads you're getting. And a multinomial probability is you've got like a die or something, okay? Another way you could think of it is roll dice rolls with an unfair die, or perhaps a big candy jar with M&Ms, big candy jar with M&Ms, and the probabilities are how the how common each color is. So, you could have a big candy jar of M&Ms and somehow like 40% of the M&Ms are red and only 10% are blue or something like that. And if you drew a handful of 10 M&Ms out of this candy jar, right? 20% yellow, 20% orange, 10% green or whatever. I don't know what the colors are. And then if you have a big candy jar and somehow 40% of them are red and you grabbed a handful of 10 M&Ms and you count up how many of each color you get, the multinomial probability could be used to describe that. Okay. So what we're going to do is we're going to say the way our documents are generated is it's like a multinomial probability, except instead of a candy jar with different color M&Ms, it's like a candy jar with a whole bunch of different words. Okay. So this is not how we create documents, but we're going to treat it like there's a big candy jar, and on each M&M candy, there's a different word. And what we're going to do is we're going to reach in this candy jar, pull out a bunch of words, and then we're going to count up how many times each word shows up. And that's going to be our document. Okay. Um, but we might, I don't know, if there's like 10,000 words in our vocabulary, okay, this is a huge candy jar, okay, and there's 10,000 different words in this candy jar, and there might be like a million pieces of candy, and the word "the" shows up like a whole bunch of times, okay, but then the word "house," there's several pieces of candy with the word house in it, but if you just grab a handful of words, you might not ever grab the word house, okay? And then some, rarer word like, I don't know, what's a infrequently used word like xylophone, okay? There might be only one or two instances of the word xylophone in this giant candy jar, and so the probability of getting the word xylophone would be very low, right? And so, if you wanted to generate this probability, um, for document building, um, your probability vector would be this really long vector, you know, length, I don't know, 10,000, okay, with the probability corresponding to each word. All right. So that's kind of the idea of how the words in our document are being generated. Okay. So you're just basically reaching into a candy jar, um, and uh, and you're grabbing the words out of there. And the idea here is that we have two different candy jars. Okay. We have a candy jar of words corresponding to document label 0. And we have a candy jar of words corresponding to document label 1. So, yeah, again, you can kind of think of it might be easier where you have like M&M candies and you have, I don't know, Skittles, I don't know. Maybe you have you have two sets of M&M candies, right? And then so you have what are they? Like if you have holiday M&M candies, let's see. Okay. So imagine, okay, you can go to Walmart and buy, okay, well this is stupid because there's only two colors, red and green. But it's the idea that all right, and then let me just I just want another M&M candy. Okay, so you have this thing, right? So now, is it possible that you reach into your regular M&M candy jar, you grab a handful, and you only get red and green M&Ms? It's possible. It's low probability, but it's possible, right? And then if you reach in here, I don't. Okay, well, this is kind of dumb because we have no other colors other than red and green. But I don't know. Are there different mixes of? Oh, look at this. You can get. But all right. But the idea is you have these different jars, right? And the different jars have different probabilities of each kind of color. And the idea is we have one jar where it looks kind of, yeah, this is a little too extreme, but it's kind of like you've got these colors in there, or these words, right? So instead of red, white, and blue here, what if you have like the words, and the words are like some of these words are like senator and president and law and things like that. And if you draw out a bag of words from this thing, you'd be like, oh, we probably drew from the politics jar. Okay. And then over here, you're drawing candies out of this jar or words out of this jar, and you're getting, I don't know, words like team and player and ball and score. And you're like, oh, we probably drew from the sports, word jar. And that's kind of the idea there. All right. So we're saying depending on the label, so we have a theta sub L, okay? Depending on the label, we draw words out from the multinomial distribution, and that's going to produce kind of our count of words there, okay? So that's what this is. So that's first we have to we kind of flip a coin using a Bernoulli to say, hey, am I drawing words out of label one, or am I drawing words out of label zero? Okay. And then depending on whether I'm drawing label one or label zero, that's going to determine which jar I'm drawing out of or which theta vector I have. And then using that, I draw the words out, and that's going to produce this document. Right? Does that kind of make sense as far as generating the document? Okay, maybe. So to make this, Bayesian, we say, well, I don't want to arbitrarily just create my vector of labels theta, and I don't want to just arbitrarily choose what my probability is for the label zero or the label one. So those things are going to get sampled from their own prior distributions. Okay, so we have a prior distribution with hyperparameters, and we're going to say, hey, um, what's the probability, when you flip the coin and it says, hey, you should draw from label zero or you should draw from label one, what should that coin probability be? Okay, that's going to get drawn from the beta distribution. Okay, you have another distribution called the Dirichlet distribution, and that would be the corresponding um, I guess like it's the corresponding prior distribution for a multinomial. So let me just kind of explain. So a beta distribution can generate values. Like if I say, hey, give me values from the R beta distribution, and I have shape parameters 5 and shape 2 equals 5. This is going to give me a bunch of random values. Let me round these off. Between 0 and 1, and here it's going to be centered around 0.322, 0.144, 0.576, okay? And you could use any of these values, like 0.322, and you could plug it in as the probability for this probability parameter in R binom, okay? But what if I wanted to generate a vector of probabilities, like 5 probabilities that add up to 1? Okay. All right. So here I thought up, I thought 0.2, 0.2, 0.1, 0.4, 0.1. But what if I wanted something like that to use here? Okay. That's where you use the R Dirichlet. Okay. our Dirichlet will generate, is this not a thing? I need to find, I always forget. All right. All right. Dirichlet distribution in R. How do I do that? Wait, I don't. Is there? Do they have MCMC pack? The Dirichlet distribution. So I think I have to load up. Okay, N and alpha. Okay. Let me see. All right. So I think I have to. I think you have to load in a library. Okay, that's fine. All right, and we're gonna try. What kind of values of alpha do I need to use? Let me see. And that didn't work. Yeah. Okay. So here is and then let me just round this off. But I could say, hey, I need a vector of five probabilities that will add up to one. Okay. And I could plug this in right here. So we have a prior distribution. Okay, we use the beta, and that's going to generate a value between 0 and 1. And the Dirichlet distribution is going to generate a vector of whatever length you specify. And all of those probabilities will add up to 1 so that you could use it with the multinomial distribution. Because again, we need the multinomial distribution is basically like we'll tell you the probability of each side of the dice or the probability of each color for the candies in the M&M jar. And, you know, how do you say like, okay, this M&M jar is, 50% green and I don't know, but it's like a mix of different colors. And you want to specify something like that, okay, you need a random distribution here. And so here, this one's 50% category 1, only around 1% category 2 and 2% category 3, 28% category 4, and 18% category 5. Okay. But this should add up, all of these things, if you say sum them, it will always sum to 1. Okay. So whatever you do, whatever probabilities you get, okay. And if you, again, whatever these things you do, they will sum to 1, but individually, you're going to get a vector of 5 different values, okay? And they can vary kind of all over the place. And you can specify, these are basically with the beta distribution, you give like kind of your prior counts. You can also give prior counts here. So you can say, I saw, word 1 50 times and word 2 30 times, and this word 10 times, and this word 5 times, and this word 1 time. And then the corresponding kind of random values that you would get might be something like this. So, 0.48 and 0.35 and 0.1 and 0.03 and 0.002 or something like that. Okay. And, here's just another random sample, kind of reflecting again. So with the beta, you'd give like your prior number of successes and failures. So like, hits and outs and so on and so forth. Um, and you do something similar here, except it's kind of prior counts for each category. You say like, I saw the color green 50 times, and I saw the color red 30 times, and I saw the color blue 10 times. And therefore, what is the kind of probabilities of each of these colors in the candy jar? And that's what we have specified here. Okay, we will continue this so we can kind of continue working through our document clustering thing, and I think it's kind of neat. So anyway, that's we'll continue that next week, but we'll wrap things up here. Have a great Thanksgiving holiday, and we'll see you next Monday.